today we're going to do oxidation reduction experiment. To cover the work that's needed for that, we're going to do some basic concepts on what is oxidation reduction. So far we've done a few different types of experiments. Reactions. We've looked at acid-base reactions in the past. We've looked at precipitation reactions. This is another type of reaction, oxidation reduction. And what is it? So that's where we're starting. So right at the beginning. So an oxidation reaction is one where a species is losing electrons. So the easiest way to explain it is to give you an example. So I'm going to draw something here for you. So if you have a beaker, you can take notes if you like, or you can just watch. And you have some copper sulfate solution in there, so aqueous. Now copper sulfate is very soluble, we did that yesterday, solubility, and so this would be blue. This would be a nice blue colour, blue solution. Now I also explained yesterday, when you see that word aqueous, we're really meaning the ions are separate. They're floating around separately. Remember I talked about that yesterday? But in chemistry is a language, so we're always using shorthand everything. So you could rewrite that formula for copper sulfate as, I'll just write it down here, AQ. It actually stands for Cu2 plus aqueous, floating around separately, and SO4, which is a polyatomic ion that you have to know off by heart, separately floating around. That's what's actually floating around in there. We just represent it like this because it's easy. So when you see that word aqueous, it means these are floating around separately as ions. You can always ask questions if you want. So if I then drop a piece of metal in here, so if this is a metal and it's zinc, we're going to drop it into the solution, you would see an instant reaction. So I'll just use a different colour. So what the result would be, and you're going to do that this afternoon to prove that this is absolutely true, is here's your beaker again with your copper sulfate, and your zinc has gone from a beautiful silver colour to a deep black now. So it's coated, it gets coated immediately. It's get a coating on it, and you start to get things falling out on the bottom from this. It just falls to the bottom. So what is happening is this metal must be more reactive than the metal in solution because a reaction occurs. If no reaction occurs, then this metal wouldn't be more reactive than the one in solution. But a reaction does occur. I'm going to write them here so you can see what's happening. So if I put zinc solid into copper sulfate solution, aqueous, this is called a metal exchange reaction. You get solid copper falling out of solution plus zinc sulfate going in, aqueous. So you can see they've swapped places. This is called metal displacement reaction or a metal exchange. I'm going to write metal displacement. Metal displacement reaction. So that's what's happening. And what that proves straight away, and this is what you're going to do with a list of metals this afternoon, is the order of those two. You can straight away say zinc must be more reactive than copper, because when you do the opposite this afternoon, so here we have two beakers, only so that I can represent what happens. And this time we're going to put a piece of copper into some zinc sulfate solution. When we put that in there, nothing will happen. And you'll go, oh, that's boring. It is. So the result would be zinc sulfate is a clear liquid, looks like water. You would have your zinc sulfate still being clear with a piece of copper floating in there. Not floating, actually sinking to the bottom. Copper, no reaction. And that tells you information as well. You don't need to do both of these. That tells you that copper is less reactive than zinc. So sometimes you get questions on exams that ask you to put metals in order based on a number of experiments. You don't need this. You don't need both of these experiments to tell you the order of zinc and copper. Only one, don't you? So there's no reaction here. That means copper is not as reactive as zinc. And there's a reaction here which tells you that zinc's more reactive than copper. So the next thing I want to show you then is this is actually called an oxidation reduction reaction as well as a metal displacement reaction. It is a metal displacement reaction, but it's also an oxidation reduction reaction. Now, in chemistry there's many names for the same thing, so it becomes a bit frustrating, but that's how it is. That's just like a language, many words for the same thing in a language. Chemistry is half language, half maths. That's why not all good maths people like chemistry, because they can't be bothered learning the language of chemistry. So this is another name, and yet another name for the same thing is redox. Redox is combining those two because chemists are very lazy and they like to truncate everything. So redox reaction. They're all names for the same thing. So this is a metal displacement reaction. It's also an oxidation reduction reaction. It's also a redox reaction. And now I'm going to show you why this is a redox reaction. We're getting to the first answer, the first question slowly. So I can now just have a look at what's going on here in what's called a half reaction. So I'm going to write it here. Half reaction. Half reactions are part of the full reaction and they cannot occur by themselves. So what's happening to the zinc is this. Zinc, solid. If we don't take any notice of the other part, is going to zinc 2 plus ions. When you separate that, remember that's shorthand, aqueous, plus 2 electrons. It's giving away 2 electrons, and that's called oxidation. Oxidation is giving away electrons, and there's a shorthand for oxidation. Of course there is. So it's O with in square brackets. That means that's an oxidation half reaction. Oxidation cannot occur without reduction. So you can never have just an oxidation reaction. You have to have a reduction reaction. That's why redox. So what is being reduced here is the copper. We're starting, in this one up here, we're starting with copper 2 plus. Do you agree? Remembering that's shorthand. We're starting with copper 2 plus. We're gaining 2 electrons from the zinc, and we're now getting copper solid coming out of solution. The gaining of electrons is called reduction, and that's our reduction half reaction. And you notice the sulfate isn't in there. It's a spectator ion. So and this is what's required in exams, all of this, when I add these 2 half equations together, I get an overall net equation. So it's called, this is so that when you get a question on this, you do the right thing. So this is called an overall net ionic equation. When I add these together, all the ones on this side of the arrow, I get, you notice that there's 2 electrons on this side and 2 electrons on this side, they're going to cancel because this is like a mathematical equation. So you get zinc solid plus copper 2 plus aqueous plus 2 electrons going to copper solid plus zinc 2 plus aqueous plus 2 electrons, and the 2 electrons can cancel, so the net ionic equation becomes zinc plus copper 2 plus aqueous goes to copper solid plus zinc 2 plus aqueous. Now I know that's a lot to take in, but you'll be able to watch this video again when you do it at the beginning of next year. And the pracs that we do are mandatory, and they will be used to ask questions, or could be used to ask questions in the external exam. So that's, and I'll just write up here so that you remember in a different colour that I'll just put it in brackets. The sulfate ions, SO4 2 minus ions, are spectator. Have you ever heard that before, that word? Spectator ions. It means they don't take part in the reaction. They're there, they just float around. They don't do anything. So you could add them back in. Wherever I see an ion, I could add the sulfate back in. So this is called a overall net ionic equation. If I wanted to, and will, so that you understand the difference, I could do the complete, or they use these words, these terminology in the exam. Net ionic equation, complete balanced equation. A complete one has the spectator back in. So it would be zinc solid plus copper sulfate aqueous going to copper solid plus zinc sulfate aqueous. It's the first time I've had to be on my knees in a lesson. There we go. What do you think? Good? Makes sense? Wow, you're very good, you people. So that is what an oxidation reduction reaction is. And to help students remember, there's a little, what do you call them? Shortcut. What do you call those words that help you remember things? An acronym, thank you. There's an acronym, oil rig. Have you heard of that one before? Oil rig. Oil rig, there's many, but I like this one. What that stands for is oxidation is loss of electrons, reduction is gain. So I'll just write that up here. Oxidation is loss of, doesn't say of electrons, but it's hoping that you know that. And that's short for electrons because, as I've already said, chemists are really lazy. So oxidation is loss of electrons, reduction is gain of electrons. Now, I think I've answered everything on this sheet. So, if you would like to have a look at the worksheet, it won't be as hard to understand, hopefully, now. So, you can see the first question says, how are oxidation and reduction defined? You can use oil rig as your definition. So I would just write straight away in there and have on my answer sheet, oxidation is loss of electrons and reduction is gain of electrons by a species in a reaction.